Hey guys, Mr. B here, and this video is the part 1 practice problems of the chapter 3.1 notes looking at accuracy, precision, error, as well as scientific notation. So, number 1, scientific notation expresses a value as the product of a number between 1 and 10 and, this is going to be some power of 10. So, it's a product for some number between 1 and 10 and a product, or I guess maybe the best way to word it is and to some power of 10. Okay, so again, it's going to be like decimal, number, decimal number times 10 to some power of 10. So all right, number 2, circle the letter of the value that is expressed as 3 times 10 to the 5th. Okay, so for scientific notation, 3 times 10 to the 5th means that it's going to be 3, and then there's going to be a decimal. Okay, even though the decimal isn't written in here, there is technically a decimal there. We're going to move it 5 places to the right, and every time we move it over a place, we need to add a 0. Okay, so 1, 2, 3, 4, 5. So this decimal, which started off here, would be 1, 2, 3, 4, and eventually end there. Okay, so our answer then, 3 times 10 to the 5th would be 300,000, which would be letter B. Okay, moving on to number 3. Circle the letter of the notation that 0.00025 could be expressed as. All right, so in this one, the decimal now is over to the left. We need to move it so that it's between the 2 and the 5, okay? So when we're done, we want this to be 2.5 times 10 to some power. And we just need to count how many places we had to move it to do that. So it starts here. So it's going to be 1, 2, 3, 4 places over. And because this number is less than 1, this is going to be to the negative 4th, not the positive 4th, which then leaves us with, again, letter B as our proper answer. Okay. Like taking a look at numbers 4, 5, 6, and 7, put these numbers in proper scientific notation. So some of these ones have decimals that are shown, others don't. If there's no decimal that you can see, the decimal's at the end. Okay, so 125,000, there would technically be a decimal here at the end. So all we're going to do is we're going to move that decimal over so that it's between the 1 and the 2. So we get 1.25 times 10, and then we just need to count how many times we had to move it. So in this case, we had to move it 1, 2, 3, 4, 5 places. So this is going to be 1.25 times 10 to the 5th. As for number 5 here, again, there's no decimal shown, but the decimal would be at the very, very end. So we're going to move it so that it's between the 6 and the 0. So our answer is going to be 6.02 times 10. Let's see if we can make this a little bit wider. There we go. Times 10. There you go. And then we just need to count how many times you had to move it. So in this case, we had to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 places over. So am I not doing that right? There we go. 6.02 times 10 to the 23rd. And we should be putting units. So like on this first one, it should be M for meters. And on this one, it should be atoms. Okay. All right. Number 6, 125 decimal 0.00000. Again, we want this decimal to be between the 1 and the 2. So this is going to be equal to 1.25 times 10. And then in this case, since the decimal is right here, we had to move it over 2 places. So this is going to be times 10 to the 2nd. Oh, geez, keep hitting buttons, my bad. Times 10 to the 2nd, and then of course, M for meters. Last one here, 0.00056. We want the decimal between the 5 and the 6. So our final answer is going to be 5.6 times 10. And we just need to count how many places we had to move it. So in this case, we had to move it over 1, 2, 3, 4, 5 places. And because this number was less than 1, it's going to be -5 instead of a +5. Okay? All right. So moving on then. Number 8, true or false. Precision is a measure of how close one measurement is to another. That is... Ooh, that's a weird way that's worded. Precision is a measure of how close one measurement is to another. That we're going to say that this is false. It's a measure of how close multiple measurements are to each other. So the way that it's worded, it kind of sounds more like accuracy. Accuracy is like looking at one measurement compared to another. Precision is looking at multiple measurements compared to each other. So we're going to say that that is false. Number 9, describe the difference between precision and accuracy. Okay, so accuracy is a measure of how close one measurement is to a reference or actual/true value. Okay, so accuracy is a measure of how close one measurement is to a reference value or an actual or a true value. Whereas precision, let's just drag this down a little bit so we can see this better. Precision is a measure of how close multiple measurements are to one another. Okay, so how close multiple measurements are to each other. All right, last 2 questions here. Number 10, determine the percent error of a balance that weighs a 500-gram mass as 458 grams. So this is a percent error problem. To find our percent error, so percent error is going to be equal to absolute value of our error. And then this is going to be, we're going to try to do our best to put an equation in here, even though it's going to look a little bit weird. Okay, so it's going to be percent error, absolute value of our percent error, divided by our accepted value, and then times 100. Okay, so in this problem, this 500 grams here, so it says determine the percent error of a balance that weighs a 500-gram mass. This 500 grams, that's our accepted value. The 458 grams, that's our experimental value. Okay, and our error here is our experimental minus our accepted. So what we're going to do is we're going to have absolute value. So we'll have 458 grams minus 500 grams. We'll take the absolute value of that. So let's again make this look proper. And we're going to divide that by our accepted value. In this case, our accepted value is 500 grams. And then we're going to times that by 100 to get it into a percentage. Okay, that is going to, oh geez, messing up everything here. That's going to be equal to, and we'll do this on a calculator real quick. So let's go 458 minus 500 divided by 500, and then times 100 to get a percentage. And I get 8.4% as our percent error. Let's back this up just a smidgen. There we go. Okay, 8.4%. That is our percent error. We'll even highlight this maybe in black just so it stands out more. Okay, 8.4%. That's our percent error. All right, last question here, number 11. Determine the percent error of a student who calculates the density of nickel to be 5.59 grams per milliliter when nickel's density is 6.44 grams per milliliter. So number 11 is also a percent error problem. It says here that the student calculates the density to be this. So this is our experimental value. And nickel's actual density is this. So this is our accepted value. Okay. So for our math, we're going to take absolute value of our error. So this is going to be 5.59 grams per milliliter minus 6.44 grams per milliliter. And then that's going to be divided by our accepted value, which is 6.44 grams per milliliter. and then times this by 100 to get a percentage. Okay, so if we do this on a calculator, we get 5.59 minus 6.44 divide by 6.44 and then times 100, and we get a percent error of about 13.2%. Okay, that is our percent error. Make this black so it stands out. Okay, so 13.2%. So that's a pretty large percent error. So, okay, anyway, so those are the first 11 questions on this first part of the practice problems for 3.1. Hopefully that helped you, but if you have any more questions or you just need more practice with percent error or scientific notation, feel free to email me, talk to me in class, reach out to me. We can do a Google Meet or something to get more practice. So, all right, guys, that's it for this one. I'm Mr. B. I'll see you in part 2 practice problems. All right, bye.